Give me 25 minutes and I will make eigenvalues click forever. We're going to move beyond seeing a matrix as just a grid of numbers. We will uncover the deep, predictive information it holds about the system it represents. This tutorial is direct, no fluff. By the end, you'll understand this. First, the core idea. You'll finally get what AV equals lambda V really means. We'll see why eigenvectors are the hidden axes of a transformation. Then, the algorithm. We'll walk through the step-by-step recipe. You know, the determinant of A minus lambda I equals 0 to find eigenvalues and eigenvectors. And finally, the application. The cool part. How eigenvalues predict the long-term behavior of a system. This is the machinery that powers everything from Google's PageRank to facial recognition. Let's get started. Quick recap. A matrix is an action. It acts on an input vector, let's call it V, to produce an output vector, V prime. As you see in the formula, V prime equals A times V. This action can be a rotation, a scaling, a shear, or a mix of all three. Let's look at a concrete example, a shear transformation. We're going to see what this matrix A does to a vector V. Our matrix A is 1, 1, 0, 1, and our vector V is 2, 3 in code. This is super simple. We'd just import numpy, then set A equals numpy.array with values 1, 1, 0, 1, and V as a numpy.array with 2, 3. The transformation is just V prime equals A at V. So what's the calculation here? We take our matrix 1, 1, 0, 1 and multiply it by our vector 2, 3. That's just 1 times 2 plus 1 times 3 for the top row, and 0 times 2 plus 1 times 3 for the bottom, which gives us the new vector 5, 3. And the output confirms it. The original vector V was 2, 3. The transformed vector, V prime, is 5, 3. Visually, the vector was bent to the right. The matrix A took our vector V and knocked it completely off its original line. The direction changed. This leads us to the central question of this entire video. Are there any special non-zero vectors that a matrix doesn't knock off their line? Are there vectors whose direction remains perfectly unchanged? The answer is yes. And now we're on a hunt for them. The hunt begins with our shear matrix, A. It's the matrix 1, 1, 0, 1. We saw it knocked the vector 2, 3 completely off its line. But what about other vectors? Let's see if we can find one that holds its ground. Let's try our first case. We'll call this one the failure. We'll test a vertical vector, V up, which is the vector 0, 1. What does our matrix A do to it? Well, we multiply our matrix A, 1, 1, 0, 1, by our vector 0, 1. So the top element is 1 times 0 plus 1 times 1, and the bottom is 0 times 0 plus 1 times 1, which gives us the vector 1, 1. The vector 0, 1 was transformed into 1, 1. Its direction was completely changed. This vector failed our test. Okay, that didn't work. But what about case 2? Let's try a horizontal vector. Let's call it V right, the vector 1, 0. What happens now? We take our matrix A, 1, 1, 0, 1, and multiply it by V right, 1, 0. For the top, we get 1 times 1 plus 1 times 0, and for the bottom, 0 times 1 plus 1 times 0. And the result is the vector 1, 0. Look at that. This is completely different. The vector 1, 0 was transformed into itself. Its direction is perfectly unchanged. What we just discovered visually are the two most important concepts in this field. Intuition number 1. Eigenvectors are directions that don't turn. An eigenvector of a matrix A is any non-zero vector V that, when you apply the transformation A, does not change its direction. For our matrix A, the vector V equals 1, 0 is an eigenvector. And what's really cool is that any other vector on that line, like 3, 0 or -5, 0, is also an eigenvector. This entire special line, in this case, the x-axis, is called an eigenspace. Okay, that's the direction. Now for intuition number 2. Eigenvalues are the stretch factors. When we found our eigenvector V equals 1, 0, the result of AV was 1, 0. How much was it stretched? Well, it was multiplied by a factor of 1. This stretch factor is the eigenvalue, denoted by the Greek letter lambda. Every eigenvector has a matching eigenvalue that tells you how much it was scaled along its line. If the absolute value of lambda is greater than 1, the vector gets stretched. If it's less than 1, it gets squished. And if lambda is negative, the vector gets flipped 180 degrees, but it still stays on the same line. Now we can put all of this together. It's time for the formalization, the eigenequation. AV equals lambda v. Let's really break this down into plain English, because this is the key. On the left, AV, we have the action of the matrix A on its special eigenvector v. And on the right, lambda v, we have is identical to simply scaling that vector v by a number, lambda. That's it. That's the whole idea right there in that beautiful little formula. So for our shear matrix A, the one we started with, 1, 1, 0, 1, 1 solution to AV equals lambda v is the eigenvalue lambda equals 1. That's the stretch factor. And the eigenvector v is the vector 1, 0. That's the direction that doesn't turn. Hunting for those special directions visually was interesting, but it's not a real strategy. What happens with a 3x3 matrix? Or a 100 by 100 matrix? We can't just look for the answer. We need a system, a process. Our goal is to find a recipe. We need to solve this equation for any matrix A. AV equals lambda v. But here is the challenge. We have two unknowns, the scalar eigenvalue lambda and the vector v. We need a clever way to untangle them and solve for one at a time. Let's start with a bit of algebra, the algebraic rearrangement. 1. We start with the eigenequation, AV equals lambda v. 2. Subtract lambda v from both sides. That gives us AV minus lambda v equals 0. And here, that 0 represents the 0 vector. Okay, step 3. Let's factor out the vector v. That should give us a minus lambda times v equals 0. And stop. Right there, we've hit a major mathematical problem. Do you see it? Look closely at that equation. A minus lambda in parentheses times v equals 0. Here's the issue. A is a matrix, a grid of numbers. But lambda is a scalar, a single number. You cannot subtract a single number from a matrix. It's like trying to subtract the number 5 from a photograph. It just doesn't make any sense. Now this is a sticking point for a lot of people, but the fix is incredibly clever. The fix is the identity matrix, capital I. The identity matrix I is the matrix equivalent of the number 1. Anything you multiply it by stays the same. So I times v is just v. Because of that, we can rewrite lambda v as lambda times I times v without changing a single thing. Lambda v equals lambda I times v. Okay, let's try that again, but correctly this time. We'll start with our intermediate step. AV minus lambda v equals 0. Now, we substitute lambda v with our new matrix-compatible version, lambda IV. So we have AV minus lambda IV equals 0. Now, we can legally factor out v. Both A and lambda I are matrices, so we get A minus lambda I, all in parentheses, times v equals 0. This is the standard form of the eigenequation, and it's the version we are going to use to build our entire algorithm. Now for the aha moment. The determinant is the key. Look at this equation. A minus lambda I times v equals 0. Let's call the matrix part m. M equals A minus lambda I. So our equation is now just mv equals 0. This equation asks a really simple question. What vector v does the matrix M transform into the 0 vector? Well, there's always one boring, trivial answer. V equals 0. Of course, m times the 0 vector is the 0 vector. That's not interesting. But remember our definition. Eigenvectors must be non-zero. So the real question is, when does mv equals 0 have a solution where v is not the 0 vector? A non-zero solution exists only if the matrix M is singular. A singular matrix is one that collapses space into a lower dimension. Think of a 2D transformation that squishes the entire plane down onto a single line. When that happens, a whole line of vectors gets mapped to the origin, giving us the non-zero solutions we need. And what is the single definitive test for a singular matrix? Its determinant is 0. This is the master key. If we want A minus lambda I times V equals 0 to have a non-zero solution for V, then the matrix A minus lambda I must have a determinant of 0. So we get our next big equation. The determinant of A minus lambda I equals 0. Look at what we just did. The determinant of A minus lambda I equals 0. The vector V has vanished for a moment. This equation, called the characteristic equation, lets us solve for the eigenvalues lambda first. We've successfully untangled the two unknowns. We now have our reliable two-step recipe. Here it is, the recipe for finding eigenproperties. Step 1. Find the eigenvalues lambda. To do this, you set up and solve the characteristic equation. The determinant of A minus lambda I equals 0. This will always be a polynomial equation, and its roots are your eigenvalues. Step 2. Find the eigenvectors V. For each eigenvalue lambda you just found, you plug it back into the standard form equation. A minus lambda I times V equals 0. Then you solve that system of linear equations to find the corresponding eigenvector V. This is the algorithm, a guaranteed process that gives us every lambda V pair that satisfies AV equals lambda V.
Alright, now it's time to stop talking and start calculating.
This is where the theory becomes a tool. Our mission? The example matrix. We are going to find the eigenproperties for this matrix A. It's a 2x2 matrix with 3, 1 in the first row and 1, 3 in the second. Now, look closely. Notice something special? This matrix is symmetric across its main diagonal. Keep that in mind. It's not a coincidence, I promise. Step 1. Find the eigenvalues lambda. Let's start with action A. Construct the matrix A minus lambda I. This is just our starting matrix A minus lambda times the identity matrix. So that's our matrix 3, 1, 1, 3 minus lambda 0, 0, 0 lambda, which gives us our new matrix 3 minus lambda 1 and 1, 3 minus lambda. Simple enough. Next, action B. Calculate the determinant. For any 2x2 matrix, the determinant is just a D minus BC. So for our matrix, we get the equation the determinant of 3 minus lambda 1, 1, 3 minus lambda equals 0. That works out to, and that brings us to action C, solve the polynomial. Cleaning that up gives us a nice, simple quadratic equation. Lambda squared minus 6 lambda plus 8 equals 0. Quick quiz, how does this factor? It factors beautifully. It becomes lambda minus 4 times lambda minus 2 equals 0. And just like that, the solutions fall right out. These are our eigenvalues. Lambda 1 equals 4 and lambda 2 equals 2. We've found them. The two special stretch factors for our matrix A are 4 and 2. This tells us that the transformation A has two special axes, and we just found out how much it stretches along them. Now for step 2. Find the eigenvectors V. Our goal here is simple. For each eigenvalue we just found, we need to solve for the vector V in our other key equation. A minus lambda I, all in parentheses, times V equals 0. Let's start with case 1. For our first eigenvalue, lambda 1 equals 4. We plug lambda equals 4 into that equation. So we have the matrix 3 minus 4, 1, and 1, 3 minus 4 times our vector xy equals the 0 vector. That simplifies to the matrix minus 1, 1, and 1 minus 1 times xy equals 0. Now for action B, solve the system. This matrix equation really just represents two lines. The first row gives us minus x plus y equals 0, which just means y equals x. The second row gives us x minus y equals 0, which also means y equals x.
Wait, the equations are identical. Is that a mistake?
No! This is a guarantee. It's supposed to happen. The system is designed to have infinite solutions because we're looking for an entire line of vectors, the eigenspace. So we just need to find any non-zero vector that satisfies y equals x. What's the simplest possible choice? Let's just say x equals 1. Well, then y must also be 1. And there it is. Our first eigenvector is v1, the vector 1, 1. All right, let's do it again for case 2. For our second eigenvalue, lambda 2 equals 2. We're going to move a little faster this time. You know the drill. We plug lambda equals 2 into the equation a minus lambda I times v equals 0. That gives us the matrix 3 minus 2, 1, and 1, 3 minus 2 times xy equals 0, which simplifies to the matrix 1, 1, 1, 1. This gives us the simple equation x plus y equals 0, or in other words, y equals negative x. So what's the simplest vector we can choose? Let x equal 1. Then y equals negative 1. Our second eigenvector is v2, the vector 1, negative 1. And we're done. For the eigenvalue lambda 1 equals 4, we found the eigenvector v1 equals 1, 1. Along the y equals x line, vectors are stretched by a factor of 4. For the eigenvalue lambda 2 equals 2, we found the eigenvector v2 equals 1, negative 1. Along the y equals negative x line, vectors are stretched by a factor of 2. But how do we know we're right? Let's verify. Does a times v1 really equal lambda 1 times v1? Left side, our matrix 3, 1, 1, 3 times the vector 1, 1. The result is 3 times 1 plus 1 times 1, and 1 times 1 plus 3 times 1, which gives us the vector 4, 4. Right side, lambda 1 times v1. That's just our eigenvalue, 4, times the vector 1, 1, which gives us the vector 4, 4. They match perfectly. The algorithm works. Remember I said our matrix A was symmetric? Here comes the payoff. Look at the beautiful results it gave us. First, the eigenvalues 4 and 2 are real numbers. There are no imaginary numbers, no complex weirdness. This is always true for symmetric matrices. Second, the eigenvectors, the vector 1, 1 and the vector 1, negative 1, are orthogonal. We can prove that with the dot product. v1 dot v2 is 0. A 0 dot product means a perfect 90-degree angle. This is also always true for symmetric matrices. You can see it right here, orthogonal eigenvectors at a perfect 90-degree angle. This clean geometry makes these matrices the bedrock of data science. They represent stable, well-behaved systems whose fundamental axes don't shear or skew.
We just went through a lot of algebra. So what? Why did we do all that work? Because eigenvalues let us predict the long-term behavior of a system. Let's look at the motivating problem, a population model. Imagine a population is split between a city and its suburbs. The yearly change is described by a transition matrix A and a state vector V. As you can see on the slide, A is the matrix with 0.95 and 0.10 in the first row, and 0.05 and 0.90 in the second. And the vector V sub k just holds the city and suburb populations for a given year k. So, to find the population after k years, we use this formula you see here. V sub k equals a to the power of k times our starting population, V sub 0. So here's our goal. Predict the state after 50 years. We need to find V sub 50. Now, calculating a to the 55th by hand is painful. And worse, it gives you zero insight into what's actually happening. There has to be a more elegant way. And there is. We know if our starting vector, v0, was an eigenvector, the problem would be easy. A to the 50th times v0 would just be lambda to the 50th times v0. But what if it isn't? Here's the key idea. For most matrices, their eigenvectors form a basis. You can think of them as a set of fundamental directions, a kind of natural coordinate system for the transformation.
So let's look at the eigenvector basis solution. For our population matrix A, we can find two eigenpairs. First, a stable state, lambda1 equals 1.0, with its eigenvector v1. And second, a decaying state, lambda2 equals 0.85, with its eigenvector v2. Because they form a basis, we can write any starting vector v0 as a mix of them. Just like in this formula, v0 equals c1 v1 plus c2 v2. Now watch what happens. 1. We start with our decomposed vector. v sub 50 equals a to the 55th times our whole expression, c1 v1 plus c2 v2. 2. We distribute the a to the 50th matrix thanks to linearity. This gives us c1 times a to the 55th v1 plus c2 times a to the 55th v2. 3. Now we use our eigenvalue magic on each part, and we get the final result. v sub 50 equals c1 times lambda1 to the 55th times v1, plus c2 times lambda2 to the 55th times v2. This is the general, powerful formula for predicting the future state of any linear system. Now for the aha moment, the dominant eigenvalue. Let's look at our formula again. v sub 50 equals c1 times lambda1 to the 55th v1, plus c2 times lambda2 to the 55th v2. Now, let's plug in our actual eigenvalues from the problem. Lambda1 is 1.0 and lambda2 is 0.85. So the equation becomes v sub 50 equals c1 times 1.0 to the 55th power v1, plus c2 times 0.85 to the 50 v2. Let's look at what these numbers become. 1.0 to the 50th power is, well, it's just 1. But what about 0.85 to the 50th power? It's approximately 0.000296. It's practically zero. You can see this effect in the visualization here. The one line stays flat, while the other just drops off a cliff. So let's rewrite our equation with these new values. v sub 50 is approximately c1 times 1 times v1 plus c2 times 0.000296 times v2. The entire second term of the equation, it just withers away. We're left with this beautifully simple result. v sub 50 is approximately c1 times v1. After 50 years, the part of our starting vector corresponding to the smaller eigenvalue, lambda2 equals 0.85, has decayed into almost nothing. The final state of the system becomes almost perfectly aligned with the eigenvector of the largest or dominant eigenvalue. The dominant eigenvector isn't just a special direction. It is the destiny of the system. No matter the initial population, if you wait long enough, the system will inevitably converge towards a state proportional to this dominant eigenvector. We didn't just solve for v sub 50. We uncovered the fundamental, stable trend buried deep inside the matrix A.
You've made it. You went from seeing a matrix as just a grid of numbers to understanding the profound story it tells. You started with a simple question. Are there any directions that don't change? And that question led you to the engine of linear algebra. So let's just take a moment to realize what you now understand intuitively. Eigenvectors are the hidden axes of a transformation, those special directions that remain stable. Eigenvalids are the stretch factors along these axes, telling you exactly how much they scale. You know that the equation determinant of a minus lambda I equals 0 is the master key to finding these values for any matrix. And most powerfully, the dominant eigenvector reveals the ultimate destiny of a system, predicting its long-term behavior. So what is your next step? It's a technique called Principal Component Analysis, PCA. Think about it like this. So far, we've found the axes of a transformation. Now I want you to ask a new, more powerful question. What are the axes of a dataset? If you look at this visualization, you can see a cloud of data points. PCA is the technique that finds the most important directions within that data. PC1, the first principal component, shows you the direction of maximum variance. This corresponds to the largest eigenvalue. Then PC2 is orthogonal to the first one, and it's the direction with the second largest eigenvalue. And here is the amazing part. The concepts you mastered in this course are the engine that drives this incredibly powerful technique. You are ready for the next step.